Hello, everyone. We're ready to start the final session of the day. We have 4 talks for you today in this session, and our first talk is going to be by Chad Norgan from Rackspace, who I know better as Beardy McBeards in the Open vSwitch channel and IRC. So, go to it.
Thank you. All right. So I'm here to kind of give you the operator perspective of what it's like to run Open vSwitch across thousands of nodes, and kind of some of the insights and kind of things we've taken away from doing that. So real quick about Rackspace, not to make a little side sales footprint or anything like that. We operate a lot of data centers, do managed hosting solutions for both cloud and having VM as well as dedicated. Then we also allow you to stitch those two together. My talk is about how operating vSwitch on a large heterogeneous fleet. And so when I'm talking about large, we're talking about tens of thousands of hypervisors. We're hosting hundreds of thousands of each virtual machines, and each of those virtual machines can attach to one or more networks. We operate as a cloud provider, we buy whatever we can, the cheapest, whether that's your Dell HPs or our OCP gear. We operate on a lot of different hardware, and so kind of the challenge of operating anything is dealing with all the different complexities you can have with each different offering. We primarily are a Zen shop. We do dabble with KVM a little bit and some containers, but primarily the focus today is going to be kind of about our Zen fleet. So we've got even on those different hardware, we actually even run on different networking configurations. So some of our gear will have 3 1 gig NICs, some will have 1 gig or 10 gig NICs, some will have 4 bonded 10 gig NICs. And so we want to have the same control system to be able to handle any of these different configurations. And then we operate a lot of different clouds in different regions. We offer 6 different public clouds all over the world, and then we run OpenStack, and the OpenStack requires a lot of control infrastructure, a lot of the control plane. We end up dogfooding and running our own internal clouds that host all of the VMs that then control the public cloud. And then, of course, we've got a lot of other environments to handle all our CI/CD or change process and making sure that we release things with a lot of testing. So, a little context about Rackspace 2. So I mentioned you could attach your VMs to several different networks. We've got these kind of little monikers for them. Our public net is basically our north-southbound, in and out of the DC. It's a publicly accessible network for the VM, and obviously we bill on the outgoing bandwidth on that. We also have another service net interface, network, which is our DC east-west network. So it handles linking to our other products. It also allows customers to do VM-to-VM communication unmetered, and then a very cheap way to move bits across the DC. And then we are also a big user of overlay networks. It's kind of probably the real reason we got into OVS in the first place. We do use NSX controllers for that, and then we do allow those to we run their gateways so you can actually stitch that overlay network in the cloud and actually bring it over if you have a workload that's not suited for cloud, let's say big DB servers. We can actually bring your cloud network all the way up to those servers. And so we've been a very early proponent of OVS. We've used it since the .9. It went into a lot of our early first-gen pre-OpenStack cloud. What was our slice host product? When we started launching and doing our OpenStack powered or our next-gen cloud, it's been used 100% on every hypervisor we have. Since that launch in August 2012, we upgraded OVS 9 times in our various environments and have landed on a lot of different versions and seen a lot of the improvements of OVS over time. So a couple real quick to give you the service provider perspective, some of the reasons and why we love using Open vSwitch. It gives us a real easy programmatic access to overlay networks and to be able to do the encapsulation. It gives us, as a service provider, I'm worried about lots of tenants sharing the same box, so I need to be able to make sure that everyone gets fair access to the physical resources, so we can implement QoS very easily programmatically, as well as for those. Kind of didn't get into it, but not all of our networks are overlay. We actually do those public and service net were bridge networks, and so on those bridge networks, it gives us a very easy way to also do the VLAN tagging, so that we make sure the traffic hits the right network. even more like port security, we want to make sure that no one's able to spoof or receive traffic they shouldn't, or kind of impersonate other traffic. So it allows us a very flexible way to make sure that all the traffic sourced from a VM's port is of that VM's and what we assign them. And then it gives us also another nice interface to do LACP bonds in our newer performance gear. And then I guess I don't think I really need to sell you this audience on the flexibility of software and why OVS is so great, but it's just been a super flexible product as our needs have changed over time, and as we've been able to move to another hardware, we've been able to mold OVS to be able to fit that platform. And if we look at those those upgrades and to get that performance benefit, if we had been doing this in hardware, there'd been no way we could have been this agile and this fast in terms of getting those performance upgrade if we were swapping out our entire switching hardware. So it's much easier to upgrade and to get to newer versions than you would if you had been buying physical devices. So kind of a look back at some of our more notable improvements. Like I said, we've been running OVS since very early, and so this is kind of tracking at least from since we've been running it in our OpenStack cloud, kind of some of our notable things we've seen that really have improved performance. Big one in 1.7 for us, as a service providers, I don't want to impact my customers when I'm doing my upgrades, and so if I can, while I'm replacing out OVS, there's a portion where I have to rip out that kernel module to put in a new one. The faster I can get that data back so that we can start forwarding packets, the better off we are. And so 1.7 got us that ability where we started saving and backing up flows and restoring those right after the KMON reload. 1.9 was another big improvement for us. That's where a lot of stuff got broken out of the main loop, most notably like logging, where we were getting into kind of very bad scenarios or loops to where so much traffic got in that we got backed up, that we were logging about the backup, and then that prevented more that created a lock to where we couldn't even do more forwarding, and we kind of get in these bad loops. So 1.9 was a big one for us that started to be the path to where we could see this as a really production ready. 1.10 for us was a real big one in that the collapsed data path with bridge networks, if we're using both a bridge that the interfaces plug into and an egress bridge that the actual physical interfaces are on, that meant we were going through OpenFlow classifications twice. And so getting that collapsed data path cut down a lot on those lookups to user space. And then we'll get into a little more on the flow eviction, but we actually got another little bump on that flow eviction, which was big for us. 1.11, we got the wildcarding, which is one of the larger improvements we saw in terms of being able to support more and more of our workloads that were having trouble. 2.0 multi-threading, and then finally with 2.1, we're actually in a really happy state. We've got all of these performance features, and now our flow eviction thresholds go up to 200,000, I think, and so we can have a lot of different disparate caches, or disparate flows cached, and it's been really beneficial for our workloads. So example, so this is smoke ping, and so this was every minute it was sending off 20 ICMP echo requests to a host. This happened to be a very, very busy Syslog collector that was collecting thousands of different host messages. And so at any given time, you've got more flows or more traffic coming in than we could get into cached in the kernel. And so we were seeing quite a bit of churn, and so that we had packet loss. And so we would see anywhere, 3 to 5, all the way to 26% packet loss in series. This is going from 1.11 to 2.1, and we see all of that packet loss drop off, and the actual round trip time stay very consistent and very tight, which is what we like. So yeah, for us, this has been 2.1 is kind of like the first OVS version. We feel we're very happy with the numbers. We've started seeing on an individual hypervisor, packets per second rates reaching about 300,000. We're easily able to saturate the NICs, even with a very dense box. Now the issues that get raised to us at an engineering level generally are, their TCP stack on the guest is not tuned for their workload, or we're starting to bump into some of the Zen net front, net back of how they kind of bring the data, from the DOM0 into the guest, and kind of running over their ring buffers. So kudos, we're really happy with where 2.1 is at now. And so some of the big kind of challenges we face in terms of how do you manage a big giant fleet of OVS, one of the primary challenges we've had is always matching the OVS kernel module of the running one, or matching the kernel module to all the kernels we have. A lot of times when we get updates for hypervisors, we don't immediately reboot those hypervisors upon installing. We obviously would if it's a big security, but if it's a performance, we will have those staged so that if something were to happen to the box and it needed to be power cycled or rebooted, it would come up on the newer updates. And so that means generally we have a state to where I have a kernel running that I need to be able to install the OVS kernel module so that I can do a kmod reload and bring them up to the new version right now, as well as I need to make sure I have the module for the kernel that it'll get on reboot. And so how do you do this when you have thousands of hosts all running different versions and at different stages of Xen patching? The only solution we've really landed on is Ansible. So it's another kind of configuration management software. Anyone in the house use Chef or Puppet? Have you ever had to run Puppet twice to get your config actually instantiated? Yeah. And so a lot of times what the problem with Puppet and these configuration managers is they don't have a good sequence of order of operations. And so what Ansible gets us to the ability to do is all of the things we could do with Puppet without an agent, and we can actually write these very complex playbooks to where we can actually go through sequences of hosts and basically kind of run through these task lists in this order. And what that means also is, like, as we're running through, if any point we catch an error on a host, we're not going to keep rolling through any of the successive or the next steps so that we can go address those one-off hosts that have a problem. It also is really, really easy to extend. So anything you can run on a Linux system, anything you can code up, basically it runs all through SSH. So you deliver your payload through SSH and you're able to execute it. You're able to modify all of the system configuration. It's a really powerful software. And so we've used that a lot, and I'll show you some of the cool, neat things we've done with Ansible in combination of OVS to where we've been able to rewire our entire public cloud and switch out where ports are at, all with a lot of confidence on how we're doing this and making sure that we're not impacting customers. So a little basics of our architecture, or at least a common SDN architecture. Previously, about a year or two ago, pretty much we had an integration bridge that was managed by an SDN controller. Every VIF plugged into that integration bridge, and that integration bridge was responsible for either encapping the traffic and sending it off to another hypervisor in the case of an overlay network, or off to a gateway to egress, or in the case of our bridge networks, it would egress through a patch port to an interface bridge, who would then put it onto the physical network. We had some scale issues with our controllers and performance to where controllers, when they did crash, took a very long time to come up, and that was an excessive downtime for our customers who weren't actually getting any of the benefit of the SDN controller when they were pretty much a bridge port and just needed to get it delivered to the wire. So we actually, about a year ago, ended up rewiring our whole public cloud to pull those bridge ports out of the SDN to let SDN do what it does best, to do all the encap and handle all the overlay networks, and then we can handle the bridge networks ourselves. And so that's basically what we did. We would create new bridges on the network or on the host. So for this one, for each of our logical networks, we'd create like a public net bridge. We'd wire that in with a patch port. And at this point, it's just sitting there dormant. And as we then went through each one of our boxes, we could look at the VIF, see what network it needed to be plugged into, and we would move it up to the appropriate bridge. And at that time, we would have already pre-calculated their flows, and we'd push it on that bridge. And then basically to make sure that they start using this patch port, we'd actually insert a higher priority, what we call a shim flow, that would overwrite the normal patch port, which would have brought it to the integration bridge. And now we're delivering their traffic up to this new bridge. And so we were able to repeat this to where it ends up being that both of our bridge ports have their little landing bridges, and then those get patched into the interface bridge and then out to the physical network. And so we've kind of approached now our SDN from like kind of a hybrid. We use on the host for our bridge ports, we use kind of a UDEV and using a lot of the Xen and VM power state hooks to be able to basically insert the flows and modify all of the different parts in Open OVS or with TC in terms of QoS to be able to control all of the OpenFlow for these ports without an SDN controller. So it's a very, very decentralized SDN controller. And then in case of our SDN controller, if you've ever used one, if your SDN controller is managing your QoS, then if you do any QoS or any TC settings outside of that controller, anytime the controller does an update, reads the state, it's going to make all of the TC on that box match what the controller thinks it should be. So to get around that, we removed all our QoS out of our SDN controller, and we're doing it on our edge with these UDEV scripts. And so we ended up inserting another bridge in front of our SDN controller, and now we present to the SDN controller that patch port is the VIF by putting the metadata on so that it thinks that patch port is the VIF, when in actuality we've actually intercepted and actually have now a bridge where we can do our OpenFlow roles to set the VLAN tag or set the QoS QID. And so it's been a really neat combination of tools to have both a very flexible rewiring given to us through OVS, as well as to have a very strong and robust config management given to us through Ansible. So we've been literally able to use this to rewire hundreds of thousands of virtual interfaces. And so doing that, part of the other reason we went to those flows, the bridge ports to manage ourselves, is we get to take full advantage of wildcarding. Our SDN controllers, they take a while to get all the OVS features ironed out. And so with ours, we could write very simple flows that did what we needed to in terms of to provide that security and QoS. And this is our Datapath flows for a few cells averaged together. And you can see after the upgrade where the end arrow is pointing, we cut our Datapath flows cached in half through the benefits of wildcarding and simple flows. So huge performance increase for us. We've also had to do this anytime we now use this technique anytime if we update those our code, our UDEV-based kind of OpenFlow. If we need to radically change that, or in the case of we came across a bug in Zen to where if data leaked to both the VIF and to the DOM0 and they both try to access the memory, the box would crash and reboot. And so we wanted to set our bridges up in secure mode. And so if you change that setting on a bridge that is not managed by a controller and it had flows, those flows go away. And so we needed a quick way to be able to enable that without doing any impact. And so we were able to use the same sort of technique of bringing up another bridge, label the old guy old, and then we'd move VIFs over across them, put their flows on, gem them on. And we can do this without dropping a single packet of traffic. And so it's been a very flexible way that we can now rewire people, change things out on the end without any sort of data path impact. And so that's kind of the fun of configuration. When I get into how we measure, we ended up writing our own kind of custom collector. And like the previous talk, the SFlow talk, we tried doing a polling. There's no way that scales. Your infrastructure changed. It's a lot of hassle. So we did a push-based method. And so periodically this script runs every minute. And it wraps a lot of the OVS stats that we were really after and publishes those to a statsd graphite host. And so we gather stuff such as the bridge, byte, packet, OpenFlow counts. We look at our data path, hit, missed, lost, and how many data path flows we have cached, as well as the Open vSwitch CPU utilization, and any of the metrics that we were after from networking on a hypervisor. And so here's what a busy DC looks like. This is probably 3,000-4,000 hosts. And this is how many data path kernel flows we have in cached. And so when we go to talking about that flow eviction threshold that used to be 2,000, that's right here. And so our normal day-to-day operating, we obviously have hosts that are above that. And so that was a huge gain for us to get that raised up, because these are people are obviously using this traffic. And so the OVS kernel was all pruning out flows that we know we were going to need to reinstall right back. And so that's more and more user space hits when we don't need them, especially when you consider that the soft eviction started down at 1,000, and so that's even lower down on that. So, and of course, we've now seen even bigger one where we start seeing people are doing scans, and this is actually what we now use to kind of pick up on DDoS or compromised hosts. That if we start seeing someone doing an abnormal amount of traffic, or in the case of when you do some SYN scanning, you show up very loud with OVS, since you are enumerating a lot of data path flows very quickly, and so you can see us taking action in the middle and cutting host out. Some more interesting data points. I thought I'd share some. This is just a SQL hypervisor, looking at the change of, we would do basically different traffic profiles and look at the his-miss loss calendars. So early on, back in, I unfortunately can't find any of the old data around our 1.7 when we were running OVS 1.7, but we used to have a lot more on the loss side where we would have packets caching up before they could actually get processed by the user space. But nowadays, we're pretty much zero on the loss, and you can kind of see the difference between the hit and miss ratios. And so we actually used a lot of that in combination to also size our cells to limit the broadcast traffic so that we can have a higher percentage of our packets get hit the fast path. And then same, we also noticed differentiation workloads by our OVS as a concept of cell or a group of hypervisors. And so we a lot of times look at this to kind of see if there's our performance hosts that deal with a lot more density. We actually see OVS use a lot more. And we'd love to see OVS over time to kind of use less and less of the system, because those CPU cycles that we're using for OVS, I can't sell to customers. And so kind of brings me to kind of where we go into the future and kind of our hopes for what's next. We're super excited to see connection tracking coming. We're looking forward to being able to do kind of a distributed firewall on all our ports. Again, like I was talking about, the more efficient performance we can get, I love performance, and multi-threading is allowed OVS to use a lot more if it needs to, but it'd be nice to, as long as, if we can get it efficient to where we're using less, that's more that we can then sell. And then we're a pretty big Python shop, and so if we're not quite a bit of developers, but I think we're going to try to get some JSON output for any of the OVS command kettles. So that'll make wrapping it and extracting the data out much easier for us. And that's all I prepared to talk about. So if you've got any questions, I'd be happy to field some.
Can you talk more on that eviction count? Like, it says 2,000. Sorry, Bhargav from Dell. Can you talk more about the eviction count? So you said 2,000, right? So that's including the mega flow enabled, or?
Yeah, I mean, that's a little historical context. So eviction threshold now in 2.1 is gone. It's been replaced with a kind of a more, I don't know, it basically is more learning, so it sees what you need and it'll increase that threshold. Basically, the eviction threshold was the kernel module. It would basically prune out cached flows when it reached this arbitrary limit. So it said, hey, I've got a hard eviction threshold of 2,000 flows I want to keep in the data path. When I start reaching 1,000, I'm going to start pruning a little more actively. When I reach 2,000, I'm going to do it very hard. And so that meant we were always, pruning out something, even though we knew later back, this box is talking to 2,000 different hosts. He's likely going to need that flow back in there in just a little bit after we prune it. And so wildcarding helped a lot, and so that was the big one. And then now that we've had in 2.1 where the flow eviction threshold goes away, it's been even better.
Bob Lance, Open Networking Lab. So I'm definitely into faster and more efficient OVS. Hopefully we'll hear a little bit about that with like DBDK and NetMap. But can't you still sell the cycles? I mean, it seems that switching cycles, you just sell them as bandwidth. I mean,
yeah.
So you showed the CPU utilization by OVS?
It was by our cell. Yeah, so it's OVS's CPU. We were tracking the process.
So how do you figure out how much of the CPU is taken by OVS?
So we've actually, on every one of those boxes, we go grab the PID of OVS, we go locate that, and then we use top to actually get the number. So we'll go look at that top and basically run a 1 second little poll on top to see what the process is using in that snapshot.
So the
of
user
time
space.
in user space,
Oh.
correct.
Frank from Cosmos. So the biggest hotspot today for you in terms of performance, so this is a guest TCP stack, or this is related to Zen, and why staying with Zen and not moving to KVM and something faster like the host?
It's very difficult to switch a multi-thousand node clusters to another thing. So we definitely are exploring other options, but we can't swap out until we have parity with what we have existing. And there's been a lot of development, a lot of man hours put in to make this work with what we have. And so it's not just as easy as saying, hey, I got this one problem, let's rip it all out and switch it out with another one where we'll find likely some problem over there. And so we take a kind of a balanced approach that we're likely going to spin up, the ability to be agnostic to the hypervisor, to where, we might have one cell that's running Zen, another one that's running KVM, another one that's running, like already we're doing bare metal provisioning that all operates still under the OpenStack umbrella. And so we'll start seeing to where these kind of workloads we'll be able to use any of them and still have the same management overarching. In terms of the Zen, we actually do have we do see some stuff on the roadmap though, in terms of the net back, net front, where they are going to improve that. So in the next version of Zens, they're going to have multiple queues or a lot of ring buffers per VIF, so you're not just one ring buffer for in and one ring buffer for out. You'll actually you can spread that wide.
Hi, this is Guru from VMware. You mentioned that you have started using containers. So how do you manage the networking of containers in your data center?
So right now, they're using our same sort of UDEV. So basically, we wrote some code that we're already getting all the metadata put into the hypervisor or the metadata store by OpenStack. So we know all of the IP address, all of the MAC, everything is already assigned and given to us at that level. And so we have a lot of places where we can hook into to program those open flows. So we use like a template-based system. So it's some Jinja templates that basically, when this container gets started up, we can very quickly shove in, here are the things to allow you to source your traffic and then to return it very quickly.
All right, that's all the time we have for questions. Let's thank our speaker.